Now we're going to take a look at one of two very particular ways that we can look at projectiles, and this is going to be horizontal projectiles. In these scenarios, we're going to be launching a projectile from some given height, and it's going to start off going horizontally and it's going to arc down. So anytime that we have a scenario where you're throwing or launching something horizontally and it's going to arc down to the ground, we would refer to that as a horizontal projectile. When you talk about horizontal projectiles, there's no acceleration horizontally. There is vertically, so we're going to still use that separation of the horizontal and vertical directions, and we're just going to deal with acceleration due to gravity in the vertical direction. So if we list out some of the variables that we'd have when we talk about horizontal projectiles, in the horizontal direction, no acceleration, but in the vertical direction, we have acceleration due to gravity, negative 9.81 meters per second squared. And since we're going to do analysis on both the horizontal and vertical directions separately, we have to identify accelerations and velocities for each of these directions separately. If we look at the vertical velocity initially, so if you're launching something initially horizontally, when it leaves the launching point, because it's moving solely horizontally, that means that at that initial condition, it has zero vertical velocity. So we can say that the initial vertical velocity is zero. And even though we don't have, and this is generic, and we haven't identified what we're launching the horizontal projectile with what velocity, no matter what, whatever horizontal velocity it starts with, it's going to be constant throughout its flight. Let's go ahead and try and demonstrate an example for this, and then we'll give you some practice so you can try it yourself. In this example, a ball is thrown out of a window 15 meters high, and it has an initial horizontal velocity of 20 meters per second. Right? So now we want to figure out how long it's going to take this ball to hit the ground. We're also going to want to determine how far it's going to travel horizontally. Whenever we start a projectile motion problem, the first step that we always do is we determine how long it takes the object to hit the ball. We know that horizontally it's going to be traveling with a constant velocity, but if we don't know how long it's in the air for, we'll never be able to tell how far it's going to travel horizontally while it's falling. So our first step in this problem is to try to figure out how long it takes to hit the ground. On the right, you see I've listed out our variables, our displacement in the y direction being a negative 15 meters, that's how far it's going to fall. Our acceleration in the y direction being a negative 9.81 meters per second squared, that's acceleration due to gravity. We have no horizontal acceleration. Our horizontal velocity is going to be 20 meters per second. And because we have no horizontal acceleration, that's going to be a constant. And initially, our vertical velocity is going to be zero. So the very first moment it's launched, it's got no vertical velocity, but because of that acceleration due to gravity, that velocity vertically is going to grow. And our first step now is we want to find out how much time it's going to take for it to hit the ground. So we're going to use an equation that relates all these variables in the vertical direction and also time. We have to do this vertically because the time it takes something to hit the ground is how long it takes it to fall. So we're going to use this equation, displacement is equal to velocity initial times time plus 1/2 at squared. And we're only going to plug into it variables that are acting in the vertical direction because that's what's going to determine the time. So our vertical displacement is going to fall 15 meters. It has zero initial velocity vertically. And then it's going to be accelerating downwards with a negative 9.81 meters per second squared. So if we plug in our values for the vertical direction here, we're going to find that we can substitute into this equation and ultimately get to a point where time squared is going to be equal to 3.06 seconds squared. Taking the square root of both sides, we'll find that the actual time it takes it to fall is 1.75 seconds. Now, I do want to point out that if you were just to drop something out of the window 15 meters high, it would take 1.75 seconds to fall. If you were to throw something out of a window horizontally, so it's just moving horizontally, irregardless of how fast it's moving horizontally, it's still going to take 1.75 seconds to fall. This is what we mean when we talk about independence of motion. How it's going to fall vertically is not going to be impacted by what it's doing horizontally. So we just treat it like a free fall drop problem, figure out how long it's going to take to fall, and then we are all set. Now that we have the time, which is the first thing we asked for, now we can figure out how far it will travel horizontally. In this scenario, I've relisted our variables. I put time in here now because it's going to take 1.75 seconds to fall. And now I want to find this horizontal distance. Since we don't have any acceleration here, we're going to use velocity equals displacement divided by time. That's the equation we use when we're not considering acceleration, because there is no acceleration. Plugging in values we have. Horizontally, it's moving 20 meters per second the whole time of the flight. It's falling for 1.75 seconds. And if we take 20 times 1.75, we end up with 35 meters.